Today I want to talk to you about delegated device authorization in the Web of Things. And yeah, in this context, I want to present to you some results from my master's project I was a part of at the University of Bremen called NAMIB, which stands for Network Access Makes IoT Better. In total, the project lasted about 2 years, actually. So there was already a first phase of the project in the bachelor's program, which was then continued in the master's program, computer science. And yeah, these two phases had 18 and 12 participants respectively, and were supervised by Carsten Bormann, Ute Bormann, and Olaf Bergmann, who, I would say are also quite well known in the IoT context. And the goals of the project in its two phases were to improve the security and the interoperability in the IoT with a focus on self-description standards. Coming to our motivation and goals. So to motivate our project, we envisioned a scenario that took place in a hotel where we envisioned that guests want to check in and of course want to access the capabilities provided by the hotel in their rooms. So in this example, IoT devices in particular. And the hotel, of course, does not want that guests can do whatever they want with the devices provided by it. So they have an interest to limit the permissions of the guests by space, so to the individual rooms of the guests, then time-wise. So the permissions to access the devices should expire once the guest has left the hotel. And finally, by scope and status. So, for example, guests should not have the same rights to access the devices as the hotel staff. Or maybe you could also think about differentiation by room status, for example, or these would be examples for a different scope per guest. And to enable a seamless interaction with the devices, the solutions we wanted to develop should be of course interoperable and should also use open standards to be also reusable, for example, in other contexts. Our project was then divided into 3 main working areas, I would say. So the working area I will present to you today dealt with authorized, the authorized device interactions themselves using the ACE OAuth, CoAP, and of course Web of Things standards. And this was, I would say, the core of the hotel scenario with the actual interactions with the devices. But there were also 2 other main working areas which would deserve their own talks, I would say. So I kind of left them out for this talk. So on the one hand, we had also onboarding solutions that were developed. In particular, one student dealt with an existing RFC or IETF's proposed standard called EAP-NOOP and developed improved solutions with less flaws called EAP-UTE, which can be used for onboarding devices. And third area dealt with restricting network access of devices and intruder detection utilizing a second self-description standard besides WoT called the manufacturer usage description, or short MUD, which is specified by an RFC 8520. But as I said in this talk, I will focus on the first area primarily. Yeah, in this area, our most important goals were to develop an interoperable solution for access the IoT devices in an authorized manner using open standards and implementations. And yeah, we also wanted, of course, to investigate potential specification improvements and contributions, and this included a better integration of ACE Auth and CoAP in general into the web of things. Yeah, before I go into the details of the implementation and our architecture, I want to briefly talk about a few specifications, namely ACE Auth, CoAP, and third one called opaque. So starting with ACE Auth, this has been recently become an ITF proposed standard as RFC 9020, and you can think about it as an adaptation of Auth 2 for constrained environments and devices. And yeah, the delegation of the authorization that I already mentioned happens by using a so-called authorization server, short AS, where both clients that want to access resources and the resource solvers themselves need to register. And yeah, the authorization server is then able to grant access to the resources via credentials, which can be used for securing either the transport or for using either transport or object security, which is specified by different profiles. So, for example, there's one for DTLS and CoAP, and one for OSCOR, which is an object security standard. And due to the fact that ACE Auth is supposed to be used in constrained environments, the access tokens are primarily encoded using CBOR, and CoAP is used as an application layer protocol, in contrast to JSON and HTTP, which are used for OAuth 2.0. The general protocol flow of ACE Auth looks like this. So after the client, which you can see on the left, and the resource server on the bottom right have established relation to the authorization server or registered with it, a client needs to request a token from the authorization server, and receives an access token, which it can use to request the actual resource from the resource server. And this resource server is then returning the resource in a protected and secure manner. And on the right, you can see an optional part of the protocol flow where resource servers are also capable of validating the credentials they received from a client. But this is an optional part of the protocol. CoAP, CoAP, which is used for the actual interactions between the different components in the protocol flow, is as a short reminder, maybe a web transfer protocol that is modeled after HTTP, which has a much lower overhead and is primarily UDP based. It enables interactions between constrained nodes and within constrained environments. And yeah, in contrast to HTTP, it also has a number of additional features built in. So an observe mechanism and multicast. And yeah, it supports transport security via DTS and object security via OSCORE. And it can also be used in with other transport protocols, for example, TCP and WebSockets, but also in theory via SMS, for example. Yeah, and last but not least, a third relevant specification we used is opaque, which we use to register and log in our guests, which is a secure, yeah, asymmetric password authenticated key exchange. And yeah, this a very nice feature of this protocol is actually that that the server does not learn the password that is used to generate the key material, which was a very interesting feature. And yeah, this protocol was then used by us for, as I said, the registration and the login. Yeah, based on these theoretical foundations, we built our architecture, which I only show partly here. As I said, I'm focusing on one of the three main areas in this talk. And yeah, the core of our architecture was the domain of the guest. So yeah, their hotel room, for example, where they were able to check in using their own client and an opaque key exchange with the authorization server, which you can see on the bottom. And oh, sorry.
I think you are not showing the very bottom part or something.
Oh, is it cropped?
Is that me? Yeah, it's cropped to the very bottom, but I.
Oh, okay.
Fine. Maybe it's fine. Yeah, now it's fine. Yeah.
Okay, great.
Yeah, now it's fine.
Okay, that's great. Yeah, and yeah, using the opaque protocol, the client was able to, or is able to check in, and using the registration with the authorization server, the client is then able to request access tokens using ACE OAuth, and yeah, can then both use or start a discovery procedure using a so-called core resource directory, which you can see on the right, and also they're able to actually access the resources hosted by the IoT devices, which are described in the WoT thing descriptions, which they're able to obtain during the discovery process. And yeah, therefore, using the login, the guest is then able to obtain a scoped access to the devices the hotel provides. Yeah, and this already brings us to our implementation. So we had 4 types of components we then used, we actually implemented. So we had an authorization server with the opaque provided check-in mechanism, the IoT devices themselves, and the guest client. And last but not least, there was also the resource directory, which we could simply reuse from a CoAP library for Python named AIO CoAP. So this was actually reusable right away. For the 3 remaining components, we developed 2 kinds of libraries. On the one hand, Rust-based ones, and on the other hand, Dart-based ones for the guest client, which was Flutter app. And so you can see that there are a couple of similarities on both sides. So on the one hand, we had decaf libraries for the ACE-auth data models and serialization and deserialization. We then created bindings to libcoap and tinydetails, which are two implementations of CoAP and DTLS in C. And we then also primarily reused an opaque crate for the opaque implementation on the Rust side. And on the Dart side, we had a similar, we had some similarities. So on the one hand, we had also a decaf library we developed. DTLS libraries were developed by us or further developed. And we also created our own WoT Things implementation, Dart WoT, which is modeled after a Node WoT, and which I will also present in a bit more detail later. And we then also contributed quite heavily to an existing CoAP library on the Dart side, and we're able to reuse an opaque library. Coming to the individual components, our authorization server was then, of course, also implemented in Rust using the decaf Rust and libcorp Rust crates. The check-in was also supported using opaque, which enabled us to generate one-time passwords, and the check-in was then able to be conducted via a QR code. There is still a web interface that is being worked on, but we didn't. We haven't been able to finish it during the project itself. So there's still a bit of work to be done, but the general registration and login flow already work, and flows already work. The individual IoT devices were also developed on a Rust basis, and we used ESP32s for that, using the ISP IDF framework and Rust bindings that are provided by Espressif, the manufacturer of the ESP boards. Ideally, we would have been able to also use the real-time operating system Riot for that, but the Rust support for Riot was a bit limited at the time, which should have been a bit different in the meantime. So I guess future projects should be able to also use Riot for that. And for the IoT devices, we were also able to use decaf Rust and use the WoT crate for the generation of the actual TDs. I think the WoT crate was already presented in a future meetup, in a past meetup by Luca. That's currently a bit of a drawback that some of the crates, or especially decaf Rusts, but also WoT require an allocator, so they can't be used in a really bare metal environment, so to say. So there's also a bit more work to be done to make the libraries more compatible with really constrained devices. But on the other hand, this allowed us to use the Rust standard library for these demonstration devices. And future work should then focus on making the libraries more compatible with constrained devices as well. I think I will skip this for now, but we can maybe come back to that later. our final component was then the guest client, which was which is a Flutter app, which was motivated by the fact that we needed UDP sockets for CoApp, and therefore we couldn't simply use a web client. Other solutions, like for example React Native, seemed a bit difficult to use, which was a bit unfortunate, since if we were able to use something like React Native, we would have also be able to reuse Node WoT, the scripting API reference implementation. But yeah, this was certainly not possible. And yeah, native Android, for example, would have also been an option, but one requirement we wanted to fulfill was also cross-platform support. And yeah, using Flutter made it relatively easy to support multiple platforms at once. And yeah, therefore we used Flutter and created our guest client with that framework, which is based on Dart, and which enabled us to support Android, iOS, Linux, macOS, and Windows, in theory at least, at the same time. And yeah, Dart had also the benefit of having a very strong type system and of compiling to native code. So these were nice benefits that using Dart also had. Yeah, on the right-hand side, you can see two screenshots of our guest client. So on the one hand, on the left side, you see the check-in mechanism, where you could either log in manually into an authorization server or also scan the QR code I've shown earlier. And on the right-hand side, you see a very rough example for a test thing that would enable us to, in this case, read out properties provided by the thing. Yeah, but using Flutter had also some drawbacks. So yeah, the library support for WoT and AceAuth was not existent, and we therefore needed to create libraries for that. And we also needed to add DTS support to the existing CoApp library. And yeah, therefore we had to also fill some gaps in this ecosystem. Yeah, a short spotlight on Dart WoT then, our Dart implementation for the Dart ecosystem of the Web of Things. So yeah, as I said, it's modeled after Node WoT and currently supports HTTP, CoApp, and MQTT. But it's currently not implementing the exposer functionality. So it's only acting as a consumer and a discoverer. But in the latter regard, it has support for security bootstrapping and various discovery methods, and also, of course, AceAuth support using decaf and the CoApp library, which we enhanced with DTS support. Yeah, I think I will skip these code examples for now as well, but we can come back to these later. Oh, maybe no. I think I will go to this example. So in order to support the AceAuth during the discovery and the discovery process and the actual interactions with the devices, we used a slightly different approach than Node WoT by defining a so-called security provider, which enabled us to define callbacks for the different credential types. And as you can see, this security provider is defined at the top and accepts a number of arguments. So first of all, it accepts the URL of the resource that is being tried to be accessed. Then, in the case of a regular interaction with the device, it accepts a form and an optional creation hint, which I should have explained maybe earlier. Yeah, so yeah. So based on the arguments that are passed to the callback, a user can define their own implementation of the token retrieval in this case, and is also capable of identifying potentially invalid credentials from first try. And this dynamic setting of credentials, in contrast to a static setting of credentials at setup, enabled us to implement the security bootstrapping mechanism. So to access a GD that is protected by a mechanism like AceAuth, for example. Using this information that is passed to the servient, library user is then able to trigger the discover process. In this case, direct discovery is used at the bottom, and is then able to iterate over the obtained thing descriptions in an asynchronous manner. The security provider I've mentioned also supports the other credential types for the defined security schemes. So, for example, PSK credentials callback can be passed, which can be used for pre-shared keys with DTLS, but also basic credentials callback for basic security when using username and password. And this I think is worked quite well as an API, which could maybe also be adapted to other implementations like WoT, for example. This already brings us to a couple of limitations and problems I wanted to discuss. So, as I said, our implementations for the IoT devices are not yet completely suitable for constrained devices. So there needs to be some adaptation to be able to use it also in these environments. Furthermore, we've noticed that the serialization and deserialization of thing descriptions is very costly for constrained devices. So maybe a different approach should be examined in the future. Furthermore, we did not implement all features of AceAuth, for example. So there's still OSCOR support missing. We could see that opaque works quite well for establishing trust to be used with AceAuth, but it is not formally specified to be usable with it yet. So there's still some standardization work needed in this regard. And last aspect is also that our results are not completely finished and published yet, but we're working on that, and hopefully you will be able to access them in our GitHub organization eventually. We'll jump to the conclusion then already. So the architecture and our implementation already work quite well. Sadly, I haven't been able to show you a demo today, but yeah, maybe that can happen in another meetup, for example. Yeah, then yeah, we're able to conclude that ACE-Auth can be used for delegated authorization in the Web of Things. However, there's still more specification and implementation work needed. For example, ACE-Auth does not have a well-defined security scheme yet. There is an example in the GD specification, but yeah, future work should actually formally specify that, and then it should be usable quite well in the Web of Things. And yeah, with that, I want to thank you for your attention for now. And at last, yeah, you can find us on GitHub, as I mentioned. We have a GitHub organization there, the NAMIB project, and there you can find the libraries we've already published and eventually also the actual applications we've developed. Yeah, thank you.
Thank you very much, Jan.